In this question, we're given a reaction X gas plus Y gas yields Z gas. And it says if the rate constant is 2.88 times 10 to the minus 3 per second at 525 K and 7.24 times 10 to the minus 2 per second at 685 K, what is the activation energy of the reaction? Well, it turns out that we can use rate constants at different temperatures in order to find the activation energy. And what we want to use is what's called the two-point form of the Arrhenius equation. And that equation is ln of K2 over K1 equals EA over R times 1 over T1 minus 1 over T2, where T1 and T2 need to be in Kelvin, which they're already given in Kelvin. So we need to plug in what we know. Well, if we call this 1 and this 2, we can now plug in. So the ln of K2 is 7.24 times 10 to the minus 2 per second. K1 is 2.88 times 10 to the minus 3 per second equals EA, which is what we're looking for, over R, which is 8.31 joules per mole K, times 1 over, in this case, T1 is 525 K minus T2, which is 685 K. So 1 over T1 minus 1 over T2 plugs in like that. Now we can do this in our calculator, and what we get is the ln of 25.1 equals EA over 8.3, I guess you should put 8.314 joules per mole K, times, we can do this in our calculator, and we get 4.45 times 10 to the minus 4 per K. Now, we could take the ln of 25.1 in our calculator, and we get 3.22 equals, now you want to multiply this by 1 over this, or just said another way, we want to take this number and divide by this number. And when we do that, we get 5.35 times 10 to the minus 5 joules per mole times EA. I apologize. This is moles per joule. Now divide both sides by this and divide into this, and what you get is the activation energy equals 60200 joules per mole, or 60.2 kilojoules per mole. So this is how you can find the activation energy of a reaction using the two-point form of the Arrhenius equation. In the next question, we want to do something slightly different. In this case, we want to find the rate constant of the reaction at 595 K. So, in order to do that, we need to consider that one of these other two is going to be 1. So what I'm going to use is this one as 1, and then I'm going to solve for this at 595 using the same equation. So the ln of K2, that's what I'm trying to find, over, using this as 1, 2.88 times 10 to the minus 3 per second, is equal to the activation energy, which I just found in joules per mole, 60,200 joules per mole, over R, 8.314 joules per mole K, times 1 over T1 is your 525K, minus 1 over T2, which is your 595. Okay. So this is basically what I want to do. Now we need to simplify the math. This math we can do all with a calculator. So if we get this, we get ln of k2 over 2.88 times 10 to the minus 3 per second equals 1.62. Take e to both sides. E to the ln gets rid of the ln. In your calculator, take e or shift ln of 1.62. And what you end up with is k2, oh, I apologize, I'm off the screen, k2 over 2.88 times 10 to the minus 3 per second equals e to the 1.62, which is 5.07. Next, cross multiply these two numbers, and what you find is that k2 equals 1.45 times 10 to the minus 2 per second. And if you look at this k, it's between this one and this one. So it's higher than 2.88 times 10 to the minus 3, and it's lower than 7.24 times 10 to the minus 2. And that makes sense because the temperature is between 525 and 685. So the two-point Arrhenius equation is useful for finding activation energies, and it prevents us from essentially using a graph, which is the other common way of doing this.